how do we know that GaN is going to provide us with transistors that are as reliable as a good old steady silicon?
You know, it's a very good point, because an engineer can get these wonderful new GaN devices and they can do magnificent things in their circuits, but if they're not reliable, the engineer can't use them. So we've spent an awful lot of time demonstrating reliability of our gallium nitride transistors. The first step, as it was told to us by our customers, is just show us that they can pass the same test that a MOSFET can pass. And so we've done tens of thousands of parts under all the traditional JEDEC type of testing: high temperature reverse bias, high temperature gate bias, humidity stressing, temperature cycling, and all the devices have done very, very well. As a matter of fact, we're not the only ones. There's several other GaN companies that show long tables of information on standard silicon MOSFET type tests with their GaN devices, and everybody passes. So the first step, it said that GaN is pretty good. But then you have to ask the question, is that valid? And should you be using the same tests for a silicon MOSFET on a new type of transistor in a new material?
That may decide to have its own ways of failing.
Right, and in order to understand that, you have to get into the physics of the failure mechanisms. So EPC has published several reliability reports. They're on our website at www.epc-co.com, and if you go to the section on reliability, you'll see 6 different reliability reports that have been done in sequence. And in the last one, we really dig into the physics of failure of gallium nitride. And gallium nitride is different from silicon. In silicon, the electrical properties are determined by impurities. In gallium nitride, the electrical properties are determined by imperfections in the crystal, which we call traps. And these traps will trap electrons. And if they trap an electron, it increases the resistance of our parts, because the electron can no longer be used for conduction. So trapping is what you have to look for in any gallium nitride device, and we have been able to measure that by stressing our devices well beyond the limits that we guarantee in our data sheet. So for example, you can see on this graph that we've stressed a 100-volt device. That's a device that we've rated at 100 volts. We've stressed it up to 130 volts. And then again at 120 and 110 and 100 volts. And we are measuring how long it takes for these devices to have a resistance that exceeds the data sheet limits. Now, just for reference, you can see a line that's drawn in green, and that's 10 years. And you can see the various curves. The black one is 1 part per million failure. So if you had 1 million parts, you would expect 1 part to fail along the trajectory of that black line. And you'll notice that at 100 volts, that's the rated maximum of the device, that black line is at about 10 to the 13 seconds, which is approximately the age of the Earth. Now, how do we do that? Well, it's very easy to actually measure the individual electrons trapping. And so we can extrapolate by watching the electrons trap. We can extrapolate when enough of the electrons are trapped that the device will exceed the data sheet. But the other thing that we can do by that is understand why these traps work. And the traps are activated by the electric field across them. And that's why at higher voltages, you'll see the failure rate is much faster. For example, at 130 volts, these things only last 10 to the 2 or 100 seconds. So what we have to do is we have to do one of two things to make our devices more and more reliable. We have to either reduce the electric field on the traps or reduce the number of traps. And here's a very interesting clue to the future of gallium nitride. Because today gallium nitride is 10 times better than silicon, but it's theoretically more than 1,000 times better than silicon. And this is the clue. Because what we've had to do in our devices is to make them bigger than they theoretically have to be in order to reduce the electric field across those traps. So we have expanded our device such that it will be reliable at 100 volts in this case.
So it sounds like you're heading in some kind of a direction akin to Moore's law, where if you can make them reliable at smaller geometries, then you've achieved a considerable breakthrough.
Exactly. That's exactly right. So if we can either decrease the number of traps or make the traps less susceptible to electric fields, we can make our devices smaller, which raises the electric field. But if the traps can stand that, that's fine. And we are more than a factor of 16 away from where we could be with our devices today. And that's the Moore's law of gallium nitride. And over the next several years, that's the direction the technology will take. Reduce the traps and make the traps withstand higher electric fields. Now, we've only shown you the stresses from the drain and to the source of the transistor. There also are stresses across the gate of the transistor. In a MOSFET, that's the most vulnerable part of the device, the gate. In a GaN device, it could also be if you haven't tested it. So in this next graph, we're going to show you the devices stressed from the gate to the source. That's the other primary way to stress the devices. And we take the device on the horizontal axis all the way up to 7 volts, although they're rated only at a maximum of 6 volts. And on the vertical axis, we plot either mean time to failure on the left-hand graph or the fit rate, which is failures in 10 to the 9th hours, on the right-hand graph. And you can see in both cases, at the rated 6 volts maximum, these parts are extraordinarily reliable, with mean time to failures once again exceeding the age of the Earth, fit rates around 10 to the minus 5. So these devices have demonstrated in all the key stress areas reliability that has never, ever been met by silicon devices. We're well beyond that.
All right, do you have any statistics that show how GaN works in actual applications?
Well, we've certainly had a lot of experience over the last 6 years that support everything that we've said. For example, we have over 10 billion device hours in actual field applications today, and of course that number is growing every day exponentially. And so far our experience in the field is failure rates of less than 0.1 fit. That's 0.1 failures per billion device hours out in the field. And that's extraordinarily good, and that's better than any silicon or silicon carbide device that I'm aware of today.
That's extrapolated from simpler data though, right?
That's actually measured. That's measured based on the number of devices we have in the field and the number of hours they've been in application. So that's not even extrapolated. That is actual.
Great.
That's actual demonstrated 0.1 fit field failure rate.
Since we're talking about real data, how is the data measured?
Well, we measure our data mostly here in our headquarters in Los Angeles, where we have extensive reliability equipment that we designed particularly to measure gallium nitride. And we have thousands and thousands of test sockets where every day we're pulling devices out of our manufacturing or out of our engineering to see how they fail, under what conditions. And using that information, we make them stronger and stronger and stronger in each new generation of products. So we are very aggressive at testing something to failure and then using that to improve our next generation of products, which also, as we mentioned, makes the devices smaller, just like Moore's law.
Thanks for sharing that. Is there more information available for people who want to dig deeper?
Absolutely, Don. If viewers want to go to www.epc-co.com, there's an entire tab on reliability, and we have 6 reliability reports in there. The most recent one is number 6.